Honors Chemistry Final Review. You can access this video and this review at srhschem.wikispaces.com. The first section is about acids and bases. First question asks us to compare the ionization of NaOH and NH3. So first, NaOH is a strong base and NH3 is a weak base. So let's look at the difference between those two. A strong base is going to ionize 100%. This means that if you drop 3 molecules of a strong base into water, each one of those molecules is going to break apart or ionize to form ions. In the case of a weak base, it's going to ionize much less than 100%. So if we started off with our 3 molecules of a weak base, maybe only one of them breaks apart. So this would be ionization of about 33%. Write an equation to show the ionization of NaOH in water. So we're going to start with NaOH, and I'm going to write it in ionic form, so Na plus and OH minus. And whenever you drop this into water, these ions are going to break apart. So we're going to get Na plus cation and OH minus anion. So whenever we write the formula, we put the H2O over the yield sign. This means that it's being added to water. And the Na plus and OH minus are going to be aqueous. Write an equation to show the ionization of NH3 in water. So this one's going to be a little bit different. We start out with our ammonia, NH3, and this time water is going to be a reactant. So I'm going to take water and I'm going to write it again in ionic form. So I have H plus and OH minus. So whenever you add the ammonia to the water, the NH3 and the H plus are going to combine, and then the OH minus will be by itself. So whenever we have NH3 and we add an extra H, we call that ammonium, which is NH4 with a +1 charge. So to write this out as an equation, NH3 ammonia and water yield ammonium, which is going to be the ion form. It has a +1 charge and it's aqueous, and hydroxide with a -1 charge, also aqueous. Draw a picture showing the correct amount of ionization for 3 molecules of NaOH. So again, we know that NaOH is a strong base, which means that whenever I add it to water, each and every molecule of NaOH is going to break apart. So we see 100% ionization. Draw a picture showing the correct amount of ionization for 3 molecules of NH3. So NH3 is a weak base. So whenever we add this to water, again, we're going to write water in its ionic form. We're going to form 1 ammonium ion and 1 hydroxide ion, but the other NH3s are going to be unreacted. So we end up with NH4 plus and OH minus, and we're going to have 2 of the ammonias that did not become ionized. Arrhenius acids and bases. So an Arrhenius acid is going to be a compound that forms H plus ions when added to aqueous solution. So hydrochloric acid, citric acid, these are going to usually have in common the hydrogen in the front. Bases are compounds that form OH minus ions when added to aqueous solution. So NaOH, calcium hydroxide, they share that hydroxide in common. So that's a good lookout to see if something is a base. According to the Brønsted-Lowry definition, an acid is going to be anything that is a hydrogen ion donor. So again, HCl fits both definitions. H2SO4, so if we take sulfuric acid and we add it to water, it's going to donate one of its hydrogens to the water and form H3O+. So because the sulfuric acid donates that H+ to water, we say that it is an acid. Bases are going to be hydrogen ion acceptors. So in the case of ammonia, the extra hydrogen is going to come from water. So in this case, water is going to donate one of its hydrogens to ammonia to make ammonium. So because water is donating, water is acting as an acid, and because ammonia is accepting, ammonia is acting as a base. Notice that they still result in more of their respective ions. So for an acid, we still get more H plus in the form of hydronium, and for bases, we still get more hydroxide. Explain why water is both an acid and a base. So if we have two water molecules, water can actually self-ionizes. So this happens to about 1 in 1 million water molecules. One water molecule can donate its hydrogen to another water molecule. This results in hydronium. The water molecule that did the donating now is short a hydrogen, so it becomes hydroxide. So one water molecule is acting as the donor of a proton, so it is an acid, and the other water molecule is acting as an acceptor, so it is a base. So according to this Brønsted-Lowry definition, water is both an acid and a base. Next question asks us to put 3 pHs in order from least to most hydrogen ion concentration. So the higher the pH, the more basic a solution is. So if something is more basic, it's going to have less hydrogen or hydronium. So that would be pH 11. It's the highest pH, which means it's the most basic. The lowest pH is going to be pH 2. This is the most acidic pH, therefore it has the most H+. And since 5 is in between 11 and 2, we would expect the hydrogen ion concentration to be somewhere between 11 and 2. A 15 milliliter sample of hydrochloric acid is neutralized by 6 milliliters of 0.25 molar NaOH. What is the molarity of the HCl? So this is a titration. Now the basis for titration, in acid-base titration at least, is whenever we are at neutral, we are at pH 7. And we know that at pH 7, the hydrogen ion concentration is equal to the hydronium ion concentration. So this is what we know about the hydrogen, or the acid rather. We know that there's 15 milliliters and we don't know the concentration. But for the base, we know that there's 6 milliliters and we know the concentration. So we're going to use the info that we know to figure out what we don't know. So the best way to do this, the way that will never fail, is to use dimensional analysis. You could use M1V1 equals M2V2, but that only works in situations where the stoichiometry is 1 to 1. So in this case it is, because we have 1 mole of HCl reacted with 1 mole of NaOH to make a mole of salt and a mole of water. But the dimensional analysis method is more reliable to get the correct answer. So let's start out with what we know. We know more about the base, so we'll start with 6 milliliters of NaOH. So in order to cancel out milliliters of NaOH, I need to put milliliters of NaOH on bottom. Now I want to get to how many moles of NaOH, so that goes on top. So this came from the molarity of the base. So we can write this 0.25 molar, we can write that as 0.25 moles per liter, or I could write it as 0.25 moles per 1,000 liters, or 1,000 milliliters. So these are both the same. So I just used that second one here so I can take care of this milliliter thing and cancel it out. You could convert 6 milliliters to liters and then use 20.25 moles over 1 liter to solve this. I just did it in one step. So now I want to go from moles of NaOH to figure out how many moles of HCl. So molarity is moles per liter. So by figuring out how many moles of HCl, I know how many milliliters of HCl, so that will get me to my concentration. So let's figure out moles of HCl. So to cancel out moles of NaOH, that needs to go on bottom, and moles of HCl should go on top. The stoichiometry is 1 to 1. We get this from the balanced equation. It's just a mole ratio. So there's 1 mole of HCl for every 1 mole of NaOH. So at this point, if I solved this problem, it would tell me how many moles of HCl. I don't want moles, I want molarity. So that means I'm going to have to take my answer here and divide it by how many liters I have. So I'm going to put milliliters on bottom because I know there's 15 milliliters. And I don't want milliliters. What I really want is liters. So milliliters will go on top and liter will go on bottom. So whenever we solve this, we end up with 0.10 moles per liter of HCl, which is the same thing as 0.10 molarity of HCl. Find the pH of a strong base. So NaOH is a strong base. What is the pH of a 0.01 molar solution of NaOH? So we want to use our pH formula here. So pH is the negative log of the hydrogen ion concentration, but we're not given the hydrogen ion concentration. What we're actually given here, this 0.01 molar, that's the hydroxide ion concentration because we're dealing with NaOH. So we can use our other formula, POH is equal to the negative log of OH minus. So whenever we plug this in, we get that the POH is 2. The question asks for the pH. So we know that if we add the POH and the pH, they should equal 14. The POH is 2. So if we do 14 minus 2, we get the pH is 12. So this question was tricky because your knee-jerk reaction is just to do that 0.01, the negative log of that, and then you would end up with 2. That's not the pH, that's the POH. Next question, compare H3O plus and OH minus. So a solution has a pH of 10 and compare the hydronium and hydroxide ion concentration. So pH 10 is basic, which means that we're going to have a lot more hydroxide ions than we have hydrogen ions. So that's what this is like over here. So this would be like pH 10 on this side, where we have lots of the hydroxide and then very little hydronium. What is formed when an acid and a base react? So if we have something like HCl, which is kind of our go-to acid, and it reacts with a base like NaOH, we're going to end up forming a salt. So there's sodium chloride, and we're going to end up forming water. So anytime you have an acid and a base, you're always going to end up with a salt and water. Now it can be different salts depending on what the acid and the base is, so it doesn't have to mean sodium chloride, but it's some ionic compound, some salt. So for example, if we had sulfuric acid and calcium hydroxide, my salt would therefore be calcium sulfate. We still make water. Which of the following act as Brønsted-Lowry acids? So remember, Brønsted-Lowry, we're looking for the proton donor, so the hydrogen ion donor. So if we look at water, in order for the C2H3O2 to become acetic acid, it needs to accept a hydrogen. So in this case, water is going to donate. On the other side, however, this hydrogen is going to be donated to the hydroxide to make water. So water and acetic acid are both hydrogen donors, making them both act as acids in this example. Next section is about gases. So first is to describe the kinetic molecular theory. So according to kinetic molecular theory, this is just a way to describe the motion of the gas particles. So the gas particles are considered to be small, hard, round spheres with insignificant volume. The gas particles are in constant, random, rapid, and straight line motion. So if you look at the animation here, we see that the particles are traveling in straight line paths until they collide with something else, in which case they're going to change their direction. And all of the collisions are elastic. That means that the total amount of energy is going to remain constant. None of it is going to be lost in that collision. Why is it easy to compress a gas but not a liquid? So gas particles are very small. We see that they have insignificant volume. So the size of a gas particle is very, very small compared to the volume that it takes up. So in other words, there must be lots of spaces between the particles in a gas. Lots of spaces means it's easy to push those molecules together. In the event of a liquid, those molecules are already very strongly attracted to each other, so they're already very close together. When they're already so close, it's difficult to compress them further because they're almost already touching. In the case of a solid, the particles are all touching, so it's very difficult to squeeze them any closer. Next question is about qualitatively what happens whenever you change different variables in the gas laws. So if temperature is constant and the pressure decreases, so this is Boyle's law, and in Boyle's law, pressure and volume have an inverse relationship. So if pressure decreases by half, the volume is going to increase by a factor of 2. 1 over 2, the inverse of that is 2. So we're going to double our volume if we decrease our pressure. In the next one, volume is constant and pressure and temperature are going to change. So this would be Gay-Lussac's law. So that's a direct relationship. As temperature goes up, particles move faster, more collisions, we get higher pressure. So if we triple the Kelvin temperature, we're going to increase the pressure by a factor of 3. We're also going to triple it. So it is very important the temperature is in Kelvin in order to apply these gas laws. Kelvin is an absolute temperature scale, so we need that to be able to compare the temperatures between different gases. The last one, pressure is constant and temperature and volume can change. So this is Charles's law. In Charles's law, volume and temperature also have a direct relationship. So if the volume doubles, the temperature must also double. So if we make the container bigger, normally that would cause the pressure to go down, but we want pressure to stay constant. So to counteract that bigger volume, we got to make it hotter so the particles collide more and the pressure stays the same. Consider the cylinders with movable pistons. So we have cylinder A with hydrogen gas and cylinder B with helium gas. How many moles of gas are present in each cylinder? So both pistons have the same conditions of pressure, temperature, and volume. So because they both have the same conditions and they're both acting as ideal gases, they have the same number of moles. You could also solve this by plugging in PV equals nRT, but since the conditions are the same, I know that the moles must be the same. What conditions would make the gas in cylinder A behave more like an ideal gas? So in an ideal gas, the particles are going to be very far apart with weak attractions. So anything that I can do to take these hydrogen particles and move them far away from each other and reduce the attraction they feel to one another is going to make it behave more ideal. So at high temperature, the particles would be moving around with so much kinetic energy that they just fly right by each other. They don't have any interaction because they're just moving too fast. So high temperature is going to reduce those interactions and make it more ideal. Low pressure. So at high pressure, the particles are going to be colliding a lot. At low pressure, the particles have to be far apart and rarely colliding. So they cannot interact with each other. So this is another way to weaken those attractions. If the conditions in cylinder A change to a pressure of 5 atm and a temperature of 300 K, what is the new volume of the gas? So we started with a pressure of 2 atm, a volume of 6.5 liters, and a temperature of 200 Kelvin. The conditions are going to change to where the pressure increases to 5 atm and the temperature increases to 300 K. So we need to figure out what is the volume going to be. So because we have variables of pressure, temperature, and volume, this is where we're going to use the combined gas law. So P1 V1 over T1 equals P2 V2 over T2. So first we're going to substitute in the numbers. So pressure 1 is 2 atm, volume 1 is 6.5 liters, and temperature 1 is 200 K. We substitute everything in on the other side. P2 is 5 atm, and T2 is 300 K, and I just left V2 as V2 because that's what we need to solve for. So next thing we'd have to do, we would cross multiply. So 2 times 6 times 300 is going to give us 3,900, and 5 times 200 gives us 1,000, so that's 1,000 V2. So we divide, and we get V2 is 3.9 liters. Hydrogen gas is collected above water at a temperature of 29 degrees Celsius. What two gases are present above the water? So you're going to have your hydrogen gas, but it's also going to be wet. It's going to be mixed in with water vapor. So here's an example. We could have a Erlenmeyer that is producing some hydrogen gas. The hydrogen gas is bubbled through water, so this is a great way to collect the gas. The test tube is going to fill up with the gas, and the gas inside, since it passed through water, it's going to be wet. It's going to have that water vapor and hydrogen gas in it as well. If the total pressure is 300 millimeters of mercury, what is the pressure of hydrogen gas alone? So the total pressure is going to be the pressure of the hydrogen gas plus the pressure of the water vapor. So we know that the total pressure is 300 millimeters of mercury, and we can look on the chart. We see that at 29 degrees Celsius, the vapor pressure of water is 30 millimeters of mercury. So whenever we solve for the pressure of hydrogen gas alone, we get 270 millimeters of mercury. Next question asks us to show the relationship between volume and pressure. So this is the Boyle's law, which is an inverse relationship. So as volume increases, the particles are less likely to collide. This causes the pressure to decrease. So the lower the pressure, the higher the volume. So we wrote that on there as an inverse relationship. Next section is about thermodynamics and kinetics. So how do each of the following influence rate of reaction? So number of collisions. If we have more particles, that means more reactions are occurring. So that would speed up the rate of reaction. The energy of the collisions. So in order for a reaction to occur, the particles must collide not only in the right way, but they also must have enough energy. So it's kind of like there's enough kinetic energy for them to stick. So more energy means that we're closer to that required kinetic energy. This will increase the rate of reaction. Collisions with walls of the container. So the container isn't a reactant. Therefore, any collisions with it isn't going to affect the rate of reaction. Angles of impact. So again, in order for particles to react, they must collide in the right way with enough kinetic energy. So if the angles of impact are in the correct orientation, product forms, and this will increase the rate of reaction. Number 18 asks us to show the relationship between temperature and rate of reaction. So higher temperature is going to mean more collisions between reactants and particles because these particles are moving faster. So those reactant particles are more likely to collide because they're moving much faster. A higher temperature also means that we are closer to that requisite amount of activation energy needed for the reaction to occur. So high temperatures will usually speed up rate of reaction. So the higher the temperature, the higher the rate. That is a direct relationship. This isn't true for every chemical reaction. There are some that are temperature dependent, especially those that occur inside living organisms. Many reactions occur at body temperature, and that's where they occur the fastest. So this is especially true for enzyme-mediated reactions, things involving proteins. But usually, especially if we're not talking about in something living, the higher the temperature, the faster the rate of reaction. So the next question is about designing an experiment to determine how surface area affects rate of reaction. So a possible claim that we can make is that higher surface area leads to more collisions, thus increasing the rate of reaction. So in order to do this, I'm going to need some magnesium with different surface areas, and we're going to react it with hydrochloric acid. And I'm going to need beakers so I can perform the reaction. I'm going to need a scale to measure out the magnesium and a graduated cylinder to measure out the hydrochloric acid. I'm also going to need to time the reaction between each type of magnesium and hydrochloric acid. So I'll need a stopwatch or a timer. A possible procedure. So you're going to need to measure out 1 gram of each type of magnesium using the scale. We want the mass to be a constant because only the independent and dependent variable should change during the course of the experiment. So obviously if I have more magnesium, it's going to take longer to react. So by controlling the mass, I'm able to compare the reaction time of each type of magnesium. Next, we need to place the different types of magnesium into their own beaker and measure out 10 milliliters of hydrochloric acid using the graduated cylinder. So again, obviously if one of them gets more acid, it's going to have a faster rate of reaction. So I also want to have a constant for the amount of acid. So I need to pour the HCl into one of the beakers with magnesium, and I want to time until the reaction is complete. So I'll know that it's done because there's no magnesium left. I'm going to do this with a stopwatch, and I'm going to record how long it takes. Then I need to repeat steps 3 and 4 with the other 2 types of magnesium. So the independent variable is what I am intentionally varying, what I'm intentionally changing from trial to trial. So that would be the surface area. We're trying to see how surface area affects the rate of reaction. So the dependent variable is what we are observing or measuring. So in this case, it's the reaction time, which is equivalent more or less to the rate of reaction. Constants are things that stay the same during each trial. I want to make sure that the only reason reaction time changed is because of surface area. So I want to be sure that the dependent variable only changed because of a change in the independent variable. So to do that, everything else besides my independent variable and dependent variable needs to be constant. So the mass of the magnesium, I want to use the same timer, the same scale. I want this to be at the same temperature. I want to use the same amount of hydrochloric acid. These are all things that can be constant, and we can come up with many more. A sample data table. So at minimum, your data table needs the independent and dependent variables in them as well as observations. So I've got my type of magnesium, that's my independent variable, and then my reaction time, my dependent variable. So next question says to determine which are endothermic and which are exothermic. So if water goes from solid, so if it goes from ice to liquid, it must absorb heat for this to happen. For water vapor to condense into liquid water, we have to lose heat. So this makes this exothermic. So remember that the solid is going to have the least amount of energy and gas is going to have the highest amount of energy. So for a solid to become a liquid, I have to absorb heat, absorb energy, that's endothermic. And for a gas to become a liquid, I have to go the opposite direction. So I have to lose energy, I have to lose heat, that's exothermic. A substance is below its freezing point and it is heated. So using the data, sketch the heating curve diagram. So here's my diagram. The time is going to go along the x-axis and temperature is along the y-axis. So the main features here, we want to look at the plateaus. So the first plateau is occurring at 18 degrees Celsius. This is where we have melting. The second plateau we see occurs around 30 degrees Celsius. This is our boiling point. So the first plateau is the phase change from solid to liquid. The second plateau is liquid to gas. So the boiling point is going to be 18 degrees Celsius and the melting point is 30 degrees Celsius. So you can figure this out either by looking at a graph or by looking at data. You're just looking for where the temperature flattens out and remains constant. Why does the temperature remain constant during a phase change? So temperature is constant, and we can also say that kinetic energy is constant. But the energy is being used to weaken the attractions between particles. So in the case of a solid, those have really strong attractions to each other. I need to weaken those attractions so we can melt into a liquid. So during a phase change, the kinetic energy is constant, but the potential energy is increasing. The most molecular motion is going to be for a gas, and the least is going to be a solid. So during a phase change, what is the energy being used to do? It is used to cause a phase change by weakening those attractions between particles. (22) asks us which way is heat going to transfer between these two blocks. So heat always transfers from hot to cold. So eventually, heat is never going to stop flowing, but eventually both blocks are at the same temperature. So the amount of heat flow is the same in each direction. So initially, block A is much hotter than block B, so heat is going to flow from A to B. Once they're both at the same temperature, heat will flow back and forth between the two of them equally in each direction. So bromine atom reacts with another bromine atom, and we form a diatomic bromine molecule. We also have energy as a product. So since energy is a product, it's being produced, that means energy is being released. We also know that the formation of a bond is always exothermic. So since all that we're doing is forming a bond from two bromine atoms into a bromine molecule, we know that this is going to be exothermic and energy is released. So entropy is a measure of the number of possible arrangements that a system can have. So the more possible arrangement of the particles, the higher the entropy. So whenever we have greater entropy, we have greater disorder. So if we look at a solid becoming a liquid, the entropy is going to increase because we're taking a solid, which is a very orderly structure, and making it into a more disordered liquid. In the case of a gas becoming a liquid, so this is where a gas, which is very disordered, is becoming more ordered as a liquid. So the disorder is decreasing, entropy is decreasing. In the case of a liquid to a solid, again, we're going from less ordered, a liquid, to a very ordered solid, so entropy is decreasing. So next one asks us to label some enthalpy diagrams. So first, we have to figure out if this is endothermic or exothermic. So reactants are higher than products, which means that for the reactants to become products, I have to lose energy. So because I'm losing energy, this is exothermic. Delta H is always the difference between reactants and products. So in this case, because I got to go from reactants down to products, the delta H is going to be negative. We are exothermic. Activation energy is from reactants to the top of the hill. So this is how much energy I need to absorb in order for a reaction to occur. So remember, bond breaking is endothermic. I have to absorb energy to break the bonds. Then bond formation is going to be exothermic. We will release that energy in the formation of bonds. So activation energy is how much energy I need in order for the reactants to break apart, to break those bonds. So it's always reactants to the top of the hill. A catalyst has the effect of making this hill smaller. So if we have a smaller hill, we also have a smaller activation energy. So this is how a catalyst speeds up a rate of reaction. It lowers that activation energy, which you can think of as a barrier to the reaction. So by making that barrier lower, more particles are more likely to have the amount of activation energy they need in order to become products. In the next example, reactants are lower than products. So in order for a reactant to become a product, it must absorb energy. So this would be endothermic. My delta H is again going to be reactants up to products. And because we're going up, it's going to be positive. We are endothermic. Activation energy is still reactants to the top of the hill. This time our difference between the reactants and the top of the hill is a little bit bigger. But that's still the energy that I need in order to break the bonds between the reactants before I can form bonds and they become products. A catalyst just makes this hill a little bit smaller, so we make our activation energy smaller. How much heat is needed to melt 15 grams of ice? So the heat of fusion, which is how much heat I need to melt the ice, is 334 joules per gram. So we're going to start with our 15 grams of ice, and we're going to put a 1 on bottom. So in order to cancel out these units, I need to have grams on bottom. And I want to figure out how much heat. So joules needs to go on top. So 334 joules are necessary to melt 1 gram of ice. So whenever we solve this, we get that I need 5,010 joules in order to melt those 15 grams of ice. Next section is about solutions. So draw the interaction between sodium chloride and water. So if you drop NaCl into water, you're going to form the sodium cation. The water molecules are going to surround this based on charge. So in water, the oxygen side tends to have a negative charge. So it's going to face the positive sodium ions. For chloride, we're going to see the opposite. So the positively charged hydrogen faces the negatively charged chloride ions. Why is sodium chloride an electrolyte, but glucose isn't? So to be an electrolyte, there are 2 conditions that we must meet. We must form ions, and those ions must be able to move. So if you drop NaCl into water, it's going to form Na plus and Cl minus ions. These ions are able to freely move in the water. So NaCl forms ions. Whenever you dissolve sugar, we break apart into sugar molecules. These molecules don't have any charges. So overall, we don't form any ions. So even though the molecules can freely move, they're not charged particles overall, so we don't have any conduction. Which chemical solubility decreases the fastest as the temperature goes from 20 to 40 degrees Celsius? So first of all, we're looking for ones with a decreasing slope. So if we look on the chart, there's only a couple that meet that condition. So we've got the HCl, and we've got this NH3, and we've got this SO2. So these guys have something in common, and they're all gases. So we know that for gases, that as we increase the temperature, solubility decreases. So this is why a hot soda will go flat before a cold soda. So the one with the steepest slope, the one with the biggest change, is going to be ammonia. A solution of KNO3 is prepared at 60 degrees Celsius, and then it's allowed to cool to 50 degrees Celsius. How much solid precipitated out of solution? So we know that KNO3 is a solid. And for a solid, usually whenever it's warmer, we can dissolve more. So we can dissolve more sugar into hot tea as opposed to cold tea. So if we look at 60 degrees Celsius, we can dissolve about 105 grams of KNO3. And if we look at 50 degrees Celsius, we can dissolve about 82 grams. So if we find the difference, that's how much is going to precipitate out. So 23 grams of solid will fall out of solution whenever we cool it from 60 to 50. What is a supersaturated solution? So this is a solution whose concentration exceeds the predicted solubility at a given temperature and pressure. In other words, I can dissolve more than I should be able to. So the way that you usually make a supersaturated solution, you make a saturated solution and then you heat it and you add more solute. Then you let it slowly cool back down. So because you heated it, you were able to dissolve more. And then whenever you cooled it back down, now that solution contains more than it should be able to. So the concentration exceeds what is predicted to be. How many moles of NaOH are needed to prepare 2 liters of a 3 molar solution? So molarity is moles per liter. So if my molarity is 3, that must mean I have 3 moles per liter. So in order to prepare 2 liters, I need to put liters on bottom to cancel. And I know that I have 3 moles in 1 liter. So whenever we solve this, we get 6 moles of NaOH. Show the relationship between temperature and solubility. So for solids, this allows more solid solute to be dissolved, increasing solubility. So for solids, as you raise the temperature, it becomes more soluble. Gases are the opposite. So heating will cause the gas solutes to escape, decreasing solubility. So high temperature means low solubility for gases. Next section is stoichiometry. So lithium reacts with aluminum chloride per the reaction below. Let's balance the chemical equation. So let's start by taking inventory. I've got lithium, aluminum, and chloride. So I've got 1, 1, and 3. And on the other side, I've got 1 of each. So the first thing that we're going to want to fix is the chloride. So if I put a 3 in front of lithium chloride, this changes these both to 3. And now I got to do the same thing on the opposite side to fix lithium. So that becomes 3. And now we're balanced. How many moles of lithium are needed to react with 5 moles of aluminum chloride? So this is just mole-mole stoichiometry. If you're going to go from moles of one thing to moles of another thing, you need a mole ratio, which comes from our balanced equation. So if I have 5 moles of aluminum chloride, I need to put moles of aluminum chloride on bottom, and I'm trying to figure out how many moles of lithium. So the mole ratio is 3 moles of lithium for every 1 mole of aluminum chloride. So this means that in order to use up all 5 moles of lithium chloride, I need 15 moles of lithium. What mass of aluminum chloride is needed to prepare 10 grams of aluminum? So in this case, we're going to go from grams of one thing to grams of another thing. So because I'm changing between 2 different chemicals, I still need a mole ratio, but I need to change the grams into moles and then the moles into grams. So we'll start with 10 grams of aluminum. In order to cancel out grams of aluminum, I need grams of aluminum on top, and I want to change it to moles. So this is where we have molar mass. Anytime you have grams and moles, that's the molar mass. So we look on our table of elements, we figure out the molar mass of aluminum, and it's 26.98 grams. So now I want to change moles of aluminum into moles of aluminum chloride. So in the balanced equation, we have mole and mole. I need a mole ratio, and the ratio between those two is 1 to 1. Now I want to take moles of aluminum chloride and change it into grams. So once again, I have grams and moles. This means I need the molar mass of aluminum chloride. So I find the molar mass of chlorine and triple it, and then add that to the molar mass of aluminum. And whenever we do this, we end up with 49.42 grams of aluminum chloride. How many grams of lithium can be produced from 2 moles of aluminum chloride? So this one, we're going to take moles of aluminum chloride and change it to moles of lithium chloride, and then moles of lithium chloride to grams of lithium chloride. So we're starting off with moles of aluminum chloride, so I need moles of aluminum chloride on bottom to cancel, and I want to get moles of lithium chloride. Once again, I have mole on top of mole, so this is a mole ratio. So the mole ratio is 3 moles of lithium chloride for every 1 mole of aluminum chloride. Now I want to take my moles of lithium chloride and convert it into grams of lithium chloride. So once again, this is going to be a molar mass, grams and moles. So you find the molar mass of chloride and add it to the molar mass of lithium. So whenever we solve this, I get 254.36 grams of lithium chloride. What is the mole ratio of lithium to aluminum chloride? So it's 3 to 1. And aluminum chloride, there's 1 mole of that for every 3 moles of lithium chloride. Next section is about equilibrium. So we have a reaction. 2 moles of A react with 1 mole of B to form a mole each of C and D and heat. And they're all gases. So what would happen if the amount of heat were increased? So whenever you add something, you need to move away from it in order to get rid of it. So adding heat or adding a chemical species, I got to move away to get rid of it. So since I add heat, I need to shift towards the reactants. So this means that once we reestablish equilibrium, we're going to have more A present than we originally did. Explain what would happen to the amount of A if C were removed. So if we were to get rid of C, so anytime you get rid of something, I need to replace it. So if I get rid of C, we're going to shift towards the products so I can replace the C that we took out. So this means that once we reestablish equilibrium, there will be less A present than there originally was. Explain what would happen to the amount of A if the pressure increased. So pressure is only going to affect our equilibrium if there are gases present. So in this case, everything's a gas. So pressure is definitely going to have an effect. So in order to figure out which way the equilibrium is going to shift, I need to look at how many moles of gas I have on each side. So on the reactant side, I have 3 moles, and on the product side, I have 2 moles. So if I increase the pressure, I have to find a way to relieve that pressure. So the way we do that is by shifting towards the side with fewer moles of gas. In this case, that would be the products. So this is to relieve that pressure. So on the product side, we've got fewer particles. We only have 2 moles of gas. So this means that if we shift to that side, fewer particles, less collisions, the pressure will go down. So that's how I would counteract an increase in pressure. So because I'm going to shift towards the products, I'm going to have less A present when the system reestablishes equilibrium. Compare the rate of the forward and reverse reactions at equilibrium. So at equilibrium, the rates of the forward and reverse reactions are going to be the same. So that's by definition what equilibrium is. So we know that that has happened whenever we see the amounts of all of the chemicals in the equation staying constant. But this does not mean that the amount of each chemical is going to be the same. So here we see this is with the reaction between hydrogen and nitrogen in order to form ammonia. So in this case, we're going to end up with more hydrogen and ammonia than nitrogen. So I know it's in equilibrium because they're constant, but it doesn't mean that they have to be equal to each other. What could you do to increase the production of product D? So anything that pushes equilibrium towards the products. So I can remove heat, C or D as they form. So this will, as I remove those, I'm going to shift towards them to replace them. If I add more A and B, I want to shift away from them to get rid of it. So this would mean more collisions between A and B, which would result in more products. So we would make more D. Or I can increase the pressure. Because the product side have fewer moles, I would shift towards that side to relieve that additional pressure. Last section is about nuclear chemistry. So which of the following is going to be a fusion reaction? So the first one, we have beta emission. So in beta emission, one of the neutrons becomes a proton. So we started off in this original hydrogen, we started off with one proton because the atomic number is 1, and we're going to have 2 neutrons because the mass number is 3. So 1 and 2 make 3. Then we changed to a helium where we have 2 protons, so that must mean there's 1 neutron. So one of those 2 protons changed into a one of those 2 neutrons changed into a proton. So this is what happens in beta emission. A neutron is made into a proton that's kept in the nucleus, and we're also going to eject a very high energy electron. So this might look like fusion because we're ending up with something that's a little bit heavier, but we're not starting with 2 things that are fusing together. Therefore, this is not fusion. The next one is going to be fission. We start with uranium-92 and we split apart to make lighter products. So that's fission. Next, this one is going to be our fusion, and we know that because our 2 light nuclei, the 2 hydrogens, fuse to form a heavier nucleus, the helium. The last one is also a fission. This is where uranium is being struck by a neutron. It absorbs that neutron, becomes unstable, and we're going to form strontium and xenon, which both have smaller atomic numbers. So we made smaller nuclei. How much time would be needed for 60 grams of an element to decay until there's only 7.5 grams left? So we know the element has a half-life of 6 days. So let's figure out how many half-lives it takes to get to 7.5 grams. So if we have 61 time, that's 1 half-life, we get 30. Half it again, that's 2 half-lives, we get 15. And if we have it a third time, we end up at our 7.5. So this means that 3 half-lives are needed. The question asks how much time would be needed. So we need to convert our 3 half-lives, put half-life on bottom to cancel, into days. So half-life cancels half-life, we end up with 18 days necessary for the 60 grams to decay to 7.5 grams. Next question says, how much of a 100-gram sample is left after 36 days? So what I need to do is I need to figure out, in 36 days, how many half-lives is that? So days needs to go on bottom to cancel, and half-life goes on top. I know that 1 half-life is 6 days, so 36 days is 6 half-lives. So I got to take 100, and I need to halve it 6 times. So once I do that, I end up with 1.56 grams remaining of the original 100-gram sample after 36 days, which is 6 half-lives. Next question, how does a nuclear power plant work? So it's very similar to how a steam locomotive works, except instead of making the steam by burning coal, we make steam by a fission reaction. So this fission reaction produces heat, and the heat is going to be transformed into different forms. So the heat is transferred to change water into steam. This steam is going to be kinetic energy used to turn a turbine. This generates electricity. Then the steam, which now has lower kinetic energy, is recondensed back into liquid water so we can pass it through the system again and reuse it. A disadvantage of nuclear power, the products of this reaction are going to include radioactive materials, and these require safe storage for thousands of years. So it's very difficult to store something like that for so long without there being accidents and things happening. So because the products are radioactive, that's a major disadvantage of nuclear power. Some study tips. First, make sure that you know when your exam is. Be sure that you are preparing on the right schedule. You should not cram the night before the final. Chances are that if you don't know it by then, cramming is probably not going to help much. So make sure that you spend that time getting a good night's sleep. You can also make a study schedule. So plan on when you're going to study for what exam. And you should focus mostly on areas of the review that you did poorly on. So sections that you really didn't understand, those are the ones where you should spend more time. Another good strategy is to look over old tests so you can do mental corrections or try to explain each answer to somebody else. So you can explain this to a real person, your cat, an imaginary friend, but that process of explaining forces you to think about the answers, and then that will help you study. You can also use srhschem.wikispaces.com for review. Good luck.